Welcome back, everyone, to another deep dive into the world of AI. We're constantly pushing the limits of large language models, and today we're going to be talking about something that's crucial for anyone actually deploying these models in the real world.
That's right, and this is really at the cutting edge of what people are thinking about right now with LLMs. It's not just about building bigger and bigger models, but about how do we actually get the most out of them once they're trained.
We're going to be digging into a survey paper on what's called test time scaling, or TTS for short. This is all about enhancing the performance of your LLMs after the training process is done, right at the point where they're actually being used.
This deep dive unpacks a comprehensive survey of test time scaling, TTS, for large language models. We're going to explore its core ideas, what aspects of the inference process can be scaled, how we go about scaling them using various techniques, where these techniques are most effectively applied across different tasks and data sets, and critically, how well we can measure the impact of this scaling.
It's a super relevant topic because we all know training these massive models can be incredibly resource intensive. So if we can find clever ways to squeeze more performance out of them without having to retrain them from scratch, well, that's a huge win.
The survey highlights a significant trend towards understanding reasoning as a decomposable process, the surprising ways different scaling techniques can work together, and a growing emphasis on finding the most efficient and broadly applicable scaling solutions for increasingly complex AI challenges. This structured overview is a vital resource for anyone looking to maximize the power of their LLMs at inference time.
The survey paper is particularly interesting because it goes beyond just listing a bunch of isolated techniques. It provides this really nice structured framework for thinking about TTS as a whole.
And that structured approach is exactly what makes this so valuable. The authors have this four-axis taxonomy: what to scale, how to scale, where to scale, and how well to scale.
It's like a roadmap for understanding the current state of TTS research and where it's headed. So let's start with the first dimension, the what of scaling. What parts of the LLM's inference process are we actually trying to manipulate here to get those performance boosts?
Right, and the survey highlights four key categories here, starting with parallel scaling.
Okay, so parallel scaling, what does that involve?
Think of it like brainstorming, where you generate a bunch of potential solutions at the same time and then try to pick the best one from that pool. The classic example here is self-consistency. You basically sample multiple outputs from the model for the same input, and then you take the majority vote.
So you're kind of leveraging the wisdom of the crowd, but in this case, the crowd is just different outputs from the same model.
Exactly. And by exploring a wider range of possibilities, you increase the chances of hitting on the right answer. But the trick is in how you generate those diverse responses in the first place.
And making sure you have a good way to combine them.
Exactly. You need robust aggregation methods to get the most out of parallel scaling.
Now, how does that compare to sequential scaling? Because that's the next category, right?
Right. Sequential scaling is more about a deliberate step-by-step approach to problem solving. Instead of generating everything at once, you guide the model through a sequence of computations where each step builds on the previous one.
Kind of like breaking down a complex task into smaller, more manageable chunks.
Precisely. And chain of thought prompting is a great example of this. You give the model a few examples of how to solve a problem step by step, and then it learns to apply that same reasoning process to new problems.
And then there are techniques like iterative refinement, where the model goes back and revises its own intermediate outputs, making it even more powerful, right?
Exactly. It's almost like the model is engaging in a more human-like, deliberative thought process.
So we have parallel scaling, which is about exploring many options in parallel, and sequential scaling, which is about carefully working through a problem step by step. Now, what about hybrid scaling?
Hybrid scaling is really interesting because it's about combining the best of both worlds. You might have a phase of parallel exploration, generating lots of initial ideas, and then switch to a more focused, sequential refinement of the most promising ones.
That sounds really intuitive.
It is, right. And techniques like tree of thoughts or graph of thoughts, where you have this branching exploration combined with in-depth investigation of specific reasoning paths, fall into this category.
It's almost like mimicking the way humans often solve problems, bouncing back and forth between divergent and convergent thinking.
That's a great analogy. And then, of course, we have the last category, which is internal scaling. This one is particularly fascinating.
Internal scaling, yeah, what's that all about?
Internal scaling is about giving the model itself more control over how much computational effort it allocates during inference.
So it's like the model can decide to think harder about certain parts of a problem.
Exactly. Models like DeepSeek R1 or some of the more recent OpenAI models, are trained in a way that lets them dynamically adjust the amount of computation they perform internally.
And how do they learn to do that?
Often, it involves training them on data sets that specifically encourage multi-step reasoning. And they also use reward modeling, where they learn to predict how good their intermediate reasoning steps are. And based on that, they can decide whether to continue processing or not.
It's like giving them a sense of self-awareness almost. They can assess their own progress and decide when they need to dig deeper.
That's a great way to put it. Okay, so we've covered the what of scaling. Let's move on to the how, the actual methods and techniques used to implement these different scaling strategies.
This is where the rubber meets the road, right? How do we actually make these models scale their inference processes?
The survey divides these methods into two main categories: tuning-based and inference-based approaches.
Let's start with tuning-based. What are we tuning here?
Tuning-based approaches involve actually modifying the model's parameters. It's about making changes to the model itself.
So we're not just changing how we use the model, we're actually changing the model itself.
Exactly. And one of the most common ways to do this is through supervised fine-tuning, or SFT.
SFT, that sounds familiar. What's the idea there?
With SFT, you essentially train the model on examples of the kind of scaled reasoning you want it to exhibit at inference time. You're explicitly teaching it how to think, step by step.
So you could, for example, create a data set of problems where the solution is broken down into a chain of logical steps and then fine-tune the model on that data set.
Exactly. And that way, the model learns to internalize those reasoning patterns. It becomes better at following those steps on its own without needing explicit prompts every time.
It's like giving the model a crash course in logic and problem solving.
That's a good way to put it. Another powerful tuning-based approach is reinforcement learning, or RL.
RL, that's a big one in AI these days. How does it apply to TTS?
With RL, instead of showing the model exactly what to do, you use rewards to guide its behavior. You essentially tell the model, hey, if you generate a reasoning chain that leads to a correct answer, you get a reward. If not, you get penalized.
So it's more like a trial and error learning process.
Exactly. The model learns to associate certain reasoning patterns with higher rewards, and it gradually gets better at generating those patterns.
And this can be done with or without an explicit reward model.
That's right. Reward model-free methods work by directly optimizing the model's policy based on the final outcome, while reward model-based methods use a separate model to predict the goodness of each reasoning step.
That's pretty neat. So with tuning-based approaches, we're basically giving the model a leg up before we even deploy it. We're either showing it examples of good reasoning or incentivizing it to discover those patterns on its own.
Yes. And now let's shift gears to inference-based approaches, where we focus on manipulating the computation that happens during inference, right as the model is generating its output.
So with inference-based, we're not changing the model itself, but we're changing how we use it, how we interact with it during that generation process.
Precisely. And the survey breaks down inference-based approaches into 4 key components: stimulation, verification, search, and aggregation.
Okay, let's unpack those one by one. Let's start with stimulation. What's that about?
Stimulation is all about encouraging the model to generate more output or more diverse output. You're trying to nudge it to explore a wider range of possibilities.
And how do you do that?
There are a few ways. You can use prompt engineering, where you explicitly ask the model to think step by step, or to consider multiple perspectives.
So just by changing the way you phrase the input, you can influence how much the model thinks about the problem.
Exactly. You can also manipulate the decoding process itself, maybe by injecting certain tokens that encourage the model to generate longer sequences, or by using techniques like self-repetition, where you make the model generate multiple samples.
It's like giving the model a little extra push to think outside the box.
And then you also have methods like mixture of model strategies, where you use an ensemble of different LLMs to generate candidates, taking advantage of their diverse strengths.
So stimulation is all about getting the model to generate a richer set of possibilities, but then we need a way to make sure that all this extra output is actually useful, right? That's where verification comes in.
Exactly. Verification is crucial. It's about evaluating and filtering those generated outputs to make sure we're not just getting more noise, but actual improvements in quality and correctness.
So how do we go about verifying these outputs?
There are 2 main types of verification: outcome verification and process verification.
Okay, what's the difference?
With outcome verification, you're checking the final answer, the end result. You might use a separate, smaller model that's specifically designed to assess the correctness of the answer. Or you might use self-consistency checks, comparing the different outputs the model generated and seeing if they agree.
It's like having a second set of eyes to double-check the work. And what about process verification?
Process verification is about checking the actual reasoning steps that the model took to arrive at the answer. This is particularly important for tasks like math or coding, where you can actually analyze the logic of each step to see if it's sound.
That makes sense. If the reasoning is flawed, then the final answer is likely to be wrong as well.
Right. And then we have search, which is a third component of inference-based scaling.
Search. So we're talking about algorithms like tree search or graph search, right?
Exactly. These algorithms allow the model to explore the solution space in a more systematic way, potentially backtracking and trying different paths until it finds a better solution. It's not just about a single forward pass. It's about intelligently navigating the space of possibilities.
It's like giving the model a map and a compass so it doesn't get lost in the vastness of the problem space.
That's a great way to think about it. And techniques like Monte Carlo tree search, or MCTS, have been really successful in this context.
And finally, we have aggregation. What does that involve?
Aggregation is all about combining those multiple outputs, whether they come from parallel sampling or from different branches of a search tree, into a single final answer.
So it's the final step in the process. You've explored all these different possibilities. Now you need to make a decision.
Right. And there are different ways to do this. You might use selection, where you simply pick the best output based on some criteria, like the highest verification score.
Yeah.
Or you might use fusion, where you actually merge those outputs together, maybe by averaging their probabilities, or by using another language model to synthesize a coherent answer from the set of candidates.
Okay, so we've covered the what and the how of scaling. Now let's talk about the where, the types of tasks and data sets where these TTS techniques are proving to be most effective.
The survey makes a distinction between reasoning-intensive tasks and general-purpose tasks.
Reasoning-intensive tasks, I'm guessing those are the ones where the model really needs to think things through step by step.
Exactly. These are tasks that require structured, multi-step reasoning and often involve rigorous verification of the solution. Things like math problem solving, code generation, game playing, scientific reasoning, those kinds of tasks.
So those are the tasks where a simple, direct answer is usually not enough. You need to see the chain of thought, the logic behind the solution.
Exactly. And then you have general purpose tasks, which are much broader in scope.
So what kinds of tasks fall under general purpose?
This could include tasks like question answering, summarization, translation, creative writing, dialogue generation tasks that often require a degree of creativity and subjective evaluation.
So it's not just about those hard, logical reasoning tasks. TTS can potentially benefit a wide range of applications, even those that are more open-ended and creative.
Right. And now we come to the final dimension of our framework. How well does scale? How do we actually measure the success and effectiveness of these different TTS methods?
How do we know if all this effort is actually paying off?
The survey outlines 4 key aspects of evaluation: performance, efficiency, controllability, and scalability.
Okay, let's break those down. Starting with performance, that one seems pretty straightforward.
Right. Performance is all about measuring how well the model is doing on the task at hand. Are the answers correct? Are the outputs high quality?
So we're talking about metrics like accuracy, precision, recall, those kinds of things.
Exactly. And they're also task-specific metrics, depending on what you're trying to measure. For example, for math problem solving, you might use metrics like pass at 1, which measures the accuracy of the first generated answer, or pass at k, which checks if at least one of the top k generated answers is correct.
So performance is about making sure the model is actually getting better at solving the problems, but then we also need to consider efficiency.
Yes, efficiency is crucial. It's about measuring the computational cost of these scaling techniques. How much time and resources are they consuming?
Because if a technique makes the model twice as accurate but takes 10 times longer to run, that's not necessarily a win.
Exactly. So we need to look at things like the number of tokens generated, the number of FLOPs required, the memory footprint, all those factors.
We want to make sure that the performance gains are worth the extra computational cost.
Right. And then we have controllability.
Controllability, what does that mean in this context?
Controllability is about how well we can manage the behavior of the model during inference. Can we constrain the length of the output? Can we ensure that the model follows certain stylistic guidelines? Can we prevent it from going off on tangents or generating inappropriate content?
So it's about making sure the model stays on track and produces outputs that meet our specific requirements.
Exactly. And there are metrics that can measure this, like the control metric or length deviation metrics.
And finally, we have scalability.
Scalability is about understanding how the performance of a particular TTS method changes as we increase the computational resources available to it.
So if we give the model more compute, more memory, does the performance continue to improve, or do we hit a ceiling?
Exactly. And we can measure this by looking at things like scaling curves, which plot accuracy against the amount of compute used.
So scalability is about understanding the potential of a particular TTS method, seeing how far we can push it.
Right. So those are the four key aspects of evaluation: performance, efficiency, controllability, and scalability.
And taken together, they give us a pretty comprehensive picture of how well a particular TTS method is working.
Exactly. And this four-dimensional taxonomy, the what, how, where, and how well of scaling, provides a really powerful framework for analyzing and comparing different TTS methods.
It's like a roadmap for navigating this rapidly evolving field.
It is. And the survey paper also goes into some really interesting detail about the overall organization and key trends that are shaping the TTS landscape.
So how is the field evolving? What are some of the big trends that are emerging?
Well, one of the most striking trends is the shift towards understanding reasoning as a decomposable process.
What does that mean exactly?
It means breaking down complex reasoning tasks into smaller, more manageable subproblems. This is what allows us to apply techniques like chain of thought prompting, iterative refinement, and search algorithms.
It's like we're taking inspiration from the way humans solve problems, breaking them down into steps, and then teaching those steps to the model.
Precisely. And this shift towards decomposition is really opening up a lot of new possibilities for TTS.
Another trend that you mentioned was the complementary nature of different TTS techniques.
Yes, that's a really important one. It's becoming increasingly clear that the best TTS solutions often involve combining multiple techniques. It's not about finding a single silver bullet, but about orchestrating an ensemble of methods that work together harmoniously.
So it's like we're building a toolbox of TTS techniques, and the best solution for a particular problem might involve using several tools in combination.
Exactly. And the survey highlights a number of examples where combining different techniques leads to significant performance gains that wouldn't be possible with any single technique alone.
So it's about understanding the strengths and weaknesses of each technique and figuring out how to put them together in a way that maximizes the overall benefit.
Right. And this leads to another important trend, which is the recognition that there's no one-size-fits-all scaling solution.
What does that mean?
It means that the best TTS approach for a particular task depends on a lot of factors, like the nature of the task itself, the size and architecture of the language model, the computational resources available, and so on.
So there's no magic formula? You can't just apply the same TTS technique to every problem and expect it to work equally well.
Exactly. And this is why researchers are increasingly focusing on developing optimal scaling strategies that are specifically tailored to the unique characteristics of each problem.
So it's about understanding the problem deeply and then designing a TTS solution that's the best fit for that particular problem.
Right. And this emphasis on optimal scaling is really driving a lot of innovation in the field.
And then you also mentioned a blurring of the lines between inference-based and tuning-based approaches. What did you mean by that?
It's becoming increasingly common to see techniques that were originally developed for one stage of the pipeline being adapted and applied to the other stage.
Can you give an example?
Sure. You might use a powerful inference-based technique, like Monte Carlo tree search, to generate a data set of high-quality reasoning examples. And then you can use that data set to fine-tune a smaller language model so it learns to perform that kind of reasoning directly without needing the expensive search algorithm at inference time.
So you're essentially using inference-based techniques to bootstrap the tuning process.
Exactly. And this cross-pollination of ideas between inference and tuning is leading to some really interesting new approaches.
The survey also provides some practical guidance for people who are interested in implementing TTS in their own work.
Yes, it does. And one of the key takeaways is that TTS can potentially benefit a very wide range of tasks, from complex reasoning challenges to more open-ended generation and real-world interactive scenarios. It's not just limited to a narrow set of applications.
So it's something that anyone working with language models should be aware of.
Absolutely. And for those who are new to TTS, the survey recommends starting with simple techniques like deliberate reasoning through prompting. It's a low-cost entry point that can already yield significant improvements.
And then as you gain more experience, you can start exploring more advanced techniques like imitation learning and reinforcement learning.
Right. And the survey provides a list of representative baseline methods that can serve as good starting points for experimentation and comparison.
And when it comes to evaluation, the survey highlights the importance of going beyond just looking at performance metrics.
Yes, that's crucial. We also need to consider efficiency, controllability, robustness, interpretability, and all those other factors that determine whether a TTS method is actually practical and useful in real-world settings.
It's not just about getting the highest score on a benchmark. It's about developing methods that are reliable, efficient, and controllable.
Right. And the survey also discusses the important trade-off between explicitly prompting for scaled reasoning at inference time versus tuning the model to perform that reasoning internally. Internal scaling can be more efficient, but it requires more upfront tuning effort.
So it's about choosing the right approach for your particular needs and constraints.
Exactly. And the survey also dedicates a significant portion to discussing open challenges and future research directions in TTS. There's still a lot of work to be done in this field.
What are some of the areas where further investigation is needed?
Well, there are a number of promising frontiers. For example, in parallel scaling, the challenge is to move beyond simple random sampling to more intelligent strategies for generating a diverse set of high-quality reasoning paths, perhaps by incorporating real-time verification signals.
So it's about being smarter about how we explore the solution space?
Right. And for sequential scaling, the focus needs to be on developing methods to maintain coherence over longer reasoning chains and prevent the accumulation of errors, maybe through more structured self-refinement processes or by integrating verification at each step.
So it's about making sure that those longer reasoning chains are actually sound and don't just lead to more confusion.
Exactly. And then for hybrid scaling, we need more generalized architectural frameworks that can seamlessly integrate parallel and sequential operations, as well as exploring the potential of multi-agent and interactive scaling in complex real-world applications.
So it's about bringing together the best of both worlds and pushing the boundaries of what's possible with TTS.
Right. And for internal scaling, there are still key challenges in ensuring effective and dynamic allocation of computational resources, maintaining the stability and consistency of reasoning without external guidance, and improving the interpretability and controllability of these more autonomous models.
So it's about making those internal scaling mechanisms more robust and transparent.
Exactly. And there are also open questions about the fundamental techniques that underpin TTS, like supervised fine-tuning, reinforcement learning, and reward modeling.
So there's still a lot we don't fully understand about how these methods work.
That's right. We need a deeper theoretical understanding of how they contribute to the effectiveness of TTS. We need to explore different types of reward models, understand their limitations, and develop new methods for combining SFT and RL.
It sounds like there's a lot of exciting research to be done in this area.
There absolutely is. And the survey also touches on the growing trend of generalizing TTS techniques across different domains, like medicine, finance, law, education, and so on.
So TTS is not just limited to general-purpose language tasks. It has the potential to revolutionize specialized domains as well.
Exactly. But there are also challenges in adapting TTS to these specialized domains, like ensuring domain-specific interpretability, integrating external knowledge, and dealing with real-world constraints.
It sounds like there's a lot of potential for TTS to have a real impact in these specialized fields, but there's also a lot of work to be done to make that happen.
That's exactly right.
Well, this has been an incredibly insightful deep dive into the world of test time scaling. The structured framework presented in this survey paper really does provide a vital roadmap for navigating this rapidly evolving field.
I completely agree.
For our listeners out there working at the forefront of AI research and development, understanding these dimensions of scaling, the what, how, where, and how well, and staying abreast of these ongoing trends is absolutely crucial for maximizing the potential of your large language models, especially as you tackle those complex and reasoning-intensive applications that are becoming increasingly important in our world.
And building on that, what's particularly exciting to me is this growing emphasis on optimal scaling that we talked about. It's not about brute force computation anymore. It's about being smart and strategic, about how we allocate our computational resources to get the most out of our models.
So it's not just about bigger models, but about smarter techniques.
Exactly. And I think that's a really important message for everyone working with language models to take away from this deep dive.
We've really just scratched the surface of this fascinating and rapidly developing field.
We have, and the survey paper itself is an incredibly valuable resource, packed with details, citations, and directions for further exploration. We encourage you to dive into the specific techniques and research directions that pique your interest.
And we would love to hear from you, our listeners, about your own experiences and perspectives on TTS. What are some of the challenges you're facing? What techniques are you experimenting with? What questions do you have?
Please share your thoughts and questions with us. Let's continue this important conversation together.
Thanks for joining us for this deep dive, everyone. Until next time.
See you then.